Rich Lund, and welcome to another episode of Indy Labs, where we put the science in your hands. Got a really important question for you. Here we go. Are we alone in the universe? Ever since humans have grasped the concept of outer space and that there's other worlds besides this one, this is probably a question that all of us at one point in time or another have considered. And honestly, I can't think of a more interesting question to ask. Well, in 1961, Frank Drake put together an equation that included all the different variables we'd have to think about in order to calculate an estimation for how many different intelligent alien civilizations are out there in our galaxy. For this thought experiment, he decided intelligent would mean capable of radio transmission communications. The equation includes variables such as how many stars are actually in our galaxy at any given time. Also, of the planets that have the right conditions for life as we know it, how many of them actually do get life going? And a really important one there at the end, of the intelligent civilizations that might be out there, how long do they last? How long does it take before something like a really large meteor, or maybe even themselves, takes them out of the game and causes their extinction? Admittedly, many of these factors are things that we don't really know, and we just have to make estimates for them. Depending upon how generous you are with your estimations, you can plug in some values that would calculate around 10,000 intelligent alien civilizations should be somewhere out there. And that's just in our own galaxy. Or if you're more strict with your estimates, you might plug in some values that would allow you to calculate that there really should only be about one intelligent civilization out there. Us. And while we're definitely capable of radio transmissions, there's still some ongoing debate as to whether or not we're intelligent. Well, for a really long time, one of the key factors in this equation, how many stars actually do have planets around them, was quite unknown. Roughly about 25 years ago, it was still quite up in the air as to whether or not a solar system like the one we have here was quite commonplace in the galaxy, or if it was actually a pretty rare and exceptional thing for stars to have planets around them. Well, in 1992, the first confirmed discovery of not just one, but two planets outside of our solar system was announced. These types of planets are called exoplanets. They are external to our own solar system. And ever since that first discovery was made, now that we knew they were out there, a lot more scientists have been on the hunt for them. As of the date of this recording, we have found over 3,600 exoplanets. Also, of all the stars we've looked at, more than half of them have had at least one planet orbiting them. And of that category of stars, about 25% of them have had multiple planets. We are very much finding that planets are pretty common in our galaxy. But how do you even find an exoplanet? Well, there's essentially two ways. First, if the planet's orbital path allows it to pass in between its star and us here on Earth, well, that means it's going to pass in front of the star from how we see it. And that causes the light coming from the star to us to dim just a little bit. And I mean a little bit. This is like looking at a spotlight and being able to detect a mosquito flying in front of it. Still, with modern telescope technology, we are able to detect such a dimness. But still, again, this only works if the planet does pass in between the star and us. But the second method actually works for practically every exoplanet we've discovered. And it's all about the star's wobble. When we talk about a planet orbiting a star, we normally just think about the very massive star's gravity pulling on that planet. But in truth, gravity is a two-way street. As the star pulls on the planet, well, that planet also pulls back on the star. So while we might talk about a planet orbiting a star, it's actually more accurate to talk about both the planet and the star, the system, orbiting a single point called the center of mass. In other words, as the planet orbits the star, it tugs on the star. And this causes the star to not just stay in one relative position, but to kind of wobble as that planet orbits it. To demonstrate this concept for you, though, a little bit better, we're going to make some models using some very easy to get a hold of at-home materials. Here's what you'll need. You're going to need a lightweight ball, something that you can push something into. These stress balls that have become popular lately work great. But if you can't find one, a small orange or a tangerine can also work. This is going to represent the star in our model. You want at least one golf tee, though having two or even three can add some excitement to this, get you some different results. You want some glue, and just about any kind will work, but the faster the drying, the sooner you'll be able to do the experiment. And then for our planets, you're going to want something smaller than your star, but also something that has some good mass to it. Something really easy for this would be marbles. And if you can, try to find two that are different sizes and thus different mass. And if you lost your marbles, well, anyway. First, select a marble to use as one of our exoplanets. I'm going to go with this red one. Kind of looks like Mars. And if you're interested in getting some different results, also select a larger, more massive one. This larger marble can serve as like a gas giant in our model. Now be careful with this next part, but put a little bit of your glue into your golf tee. Glue your marble then to the tee. Hold it in place until it dries a little bit. Once it's holding on its own, set it someplace where it can dry without causing a mess anywhere. And go ahead and apply glue to your second one. This one here shall be our gas giant. Okay, we'll leave those undisturbed for a while. Once you know for sure that it's dry, we're ready to assemble our model. Somewhere on your stress ball, we're going to insert the golf tee by just pushing it right in. Might need to wiggle it a little bit. Make sure once it's in though, it's not pressed in all the way, just enough so that way it won't easily come out. You want some length there to represent the distance that planet is from its star. Now we are ready to model the idea. Before we actually show the modeling though, let's give the star a spin without a planet around it. Notice there's not really any perceivable wobble. Now, let's put our planet back in. Let's test it with an exoplanet. Are you noticing a wobble? As it spins, really, this whole thing, golf tee included, is our system. And so as it's rotating, it's really attempting to spin around that center of mass, which is no longer at the very center of our star. A center of mass is the average position where all of the mass would be. It's an imaginary point. So if we increase the mass by switching out which planet we're using, that center of mass is actually going to be more in between our two objects. So in theory, we should get more of a wobble from our more massive planet. Definitely more of a wobble. And that is your exoplanet wobble model. Cool, huh? So did you notice that the heavier the planet was in our exoplanet wobble model, the more that star ended up wobbling? That's a really strong part of this model because that's exactly what happens with exoplanets as well. By measuring the actual radius that these stars wobble, astronomers can calculate how massive the planet must be in order to cause that amount of wobble. Hey, I hope you had fun with this exoplanet wobble model. And I also hope maybe you can use it to teach somebody else about what exoplanets are and how we look for them. We've got many more Indy Labs on the horizon, so if you enjoyed this one, be sure to subscribe to the channel so you don't miss out on any of them. Oh, and also, at the end of this video, why don't you check out this awesome exoplanet wrap that my friend Comaniti put together. Now that guy knows how to wobble. And while I don't have an answer to the Drake equation, still, I think it's pretty awesome to see that we're making progress towards pinning down and really getting to know better one of the factors we'll need to figure out in order to someday solve it. And hey, if it is just us out here in the galaxy, well then doesn't that just make it even more important why we should all work together? So that way someday, when we're ready, we can go explore what Kepler and other telescopes have shown us is a huge, wonderful playground just waiting for us. I'm Rich Lund. I'll catch you next time.